Alright, I'll be talking about the top module. So in this top module, we have various wires that are the flags and the inputs, outputs, and the data buses that will be transporting the various things around our microcontroller. The next major segment is the program counter. So this will increment every clock cycle, and when it reaches every multiple of 4, that's when it'll actually start the next instruction. So instead of, we're essentially dividing by 4 our actual clock frequency, but because some things take longer than others, we'll actually not increment by 1. I'll show you in a little bit. We then are essentially in our instruction memory that essentially stores the actual code that we're running. And then we have all of this programs that are doing the program counter. So these are the things I was talking about, where some things like branching, jumping, and stepping will take different amounts of time, and therefore we will jump them in different ways. This is also where we take care of doing a sign extension and a 0 extension, which are necessary to make sure that we fit in our 32-bit wide buses. This is also where we are extracting various jump locations and our branch locations. We then have our control unit, which actually generates those flags. So we have flags for things like, are we writing to memory? Are we reading from memory? What ALU source are we using? Is it like an immediate, or is it from another register? This control unit will take care of that. We are then actually deciding what register address we're loading and where we want that to be stored. So that's some of the things that we stated earlier. We have a jump register controller. This is if we're doing the jump register command, we need to tell it to load it, and that's what we want to look at. Our ALU controller essentially just tells us what operation we're doing, whether it's addition, multiplication, division, subtraction, and the ALU will actually perform that operation, give us the output, and depending on various inputs, whether we chose immediate or register, it'll determine what we actually input into the ALU. Our data memory is then used for both the RAM of the ALU for storing things for long computations, and it's also used for storing in deep memory for more complex software. Lastly, we have one of the peripheral bus options. So this is an LED peripheral bus, very simple. It will be described later in the video, but essentially we're passing in data, and when it notices that we're trying to talk to it, then it will start paying attention and start listening.
So one of the files I worked on was the peripheral bus. A peripheral bus essentially allows the processor to read in and write data to whatever the microcontroller is attached to. And in our case, it's the LEDs on the FPGA board. So as you can see, essentially what it is it's a finite state machine. If the reset button is pressed, then all the values reset. Otherwise, the state just moves to its next state. And the next state logic is described here, where if it is the reset, it will reset itself. It will reset the index of the device that it's indexing from. The next state will then go to the device select. If it is already on the device select, it will either select as receiving data or sending data, so either read or write. And if it's supposed to send data, then it's just going to send data here. Essentially, the next state is just going to wait for the acknowledgement from the processor.
So this is our ALU. It's responsible for all arithmetic and logical operations of our processor. As you can see, it has add, subtract, and or if less than multiply and divide functionality. And essentially, it takes in two 32-bit inputs, does whatever you need it to do, and then raises any flags corresponding to those operations if you need it. So, just to give a few examples, here you can see we have the add functionality, and essentially we're just carrying out that operation, and then for each operation we have some logic to handle the flags that do need to be raised for those operations. To give an example, let's say we want to divide by something. If we are dividing a by b and b is 0, then we set the divide by 0 flag. and if not, then we just proceed with that operation.
For our microcontroller, we decided to use a modified MIPS instruction set. We have three different types of instructions. First is our register-register type, which includes two different source register and a third destination register. Next is our I type. Our I type includes a source register, a destination register, and finally an immediate or otherwise known as an integer. Finally, it's our jump type, which just includes our target address. My job on the team is to assemble these instructions into binary for our microcontroller. Let's take a look at how this is done. This is done using this Python script. There are 4 different parts to this script. The first is fetching the data. We do this using UART. After the file is included, it is passed through the assemble MIPS file function, which breaks the file into different lines and sends these lines to our assemble MIPS function. This function uses our predefined dictionaries to map the instructions to the associated binary. Let's take a look at how this is done. Here we have our input.txt file, which contains the instructions that we would like to send to our microcontroller. If we run the script, we will see that an output.txt file is generated. This file includes our assembled binary.
This is very simple assembly code for adding two numbers. In this case, they are the same number, but we're storing the number in register 2, and then we're storing the number in register 3. We're adding them together, and then we are displaying them by reading from the register that they are saved to. So to demonstrate our microcontroller, we're going to do a very basic operation where we're going to add two numbers. It's already showing the display on the board because it happened so quickly because our clock runs at 200 megahertz. But I will click the reset so you can actually see it happening instantaneously. You already saw the code, but it essentially has these two numbers and displays it. And nothing, you won't be able to see it because it's doing all the operations incredibly quickly, but that is the output of the program. All right, so to prove that our computer is reprogrammable, we uploaded a different set of firmware, and this one is the Fibonacci sequence. This is the code for the Fibonacci sequence. So what it does is it has a blank instruction to make sure that the CPU is completely ready for actually starting the code. And then we are loading variables into first what number we want to stop at, and then the two starting numbers, so 0 and 1. We are then adding our sum is the sum of A and B, essentially. And then we are setting B equal to A and A equal to the sum. Then we are displaying that sum. And then we are checking, is our sum equal to our stop condition? If it is, we will jump out of the program. If not, we will continue. And if we continue, we go on to step 10, which just jumps up in the program to then redo the summation and continue our Fibonacci count until we reach our termination condition. And we're also showing it in a different mode where instead of the program counter is incrementing with the clock, you're able to increment it with pushing a button. So I'm going to demonstrate it counting up in the Fibonacci sequence. There are several startup requirements, like storing some variables, storing a stop condition, and starting to increment. But you'll see that as I'm slowly pushing through, you're adding the numbers, storing them, and then displaying them. And it will continue to add up the Fibonacci sequence.
And this is our last demonstration. This is a much simpler program, but it just demonstrates even more variety in terms of what the microcontroller can do. So this is just an XOR between two numbers. Again, walking through the program counter, we can see that it provides the XOR of the two numbers that we fed in.